Hey there, college algebra folks. Back here with another video in section, in our study of the systems of linear equations and using matrix methods to find their solutions, where we are going to deviate a little bit off that task for just the moment in this section, where we spend a little bit more time working with matrices, right? Working with these things we know as matrices, performing some of the fundamental operations that we can perform with these matrices. And what do I mean by those fundamental operations? They are the operations that we see going on here. Those operations known as scalar multiplication, the operation known as matrix addition, right? The operation we can see highlighted here where we might note we can take the addition of a multiple of matrices, or a difference for a multiple of matrices involving that minus. And then we can find these products seen down below here, which are known as the dot product of matrices, right? So we can perform these respective calculations, and this section is going to focus in on performing these types of operations with matrices. So what we have here in question number one is question one is just, here we have these two matrices, matrix U and matrix V, and we're asked to perform these operations on them, where this first operation is telling us to take matrix V and form what would be 5 times matrix V, form a scalar multiple of matrix V. What we might take note on here, right? Let's take note here just to begin with. Let's bring this down into its own sheet of paper here. Matrix V is equal to the matrix 1, -9, -3, 10, right? And we're being asked to evaluate, right, what would be 5 times matrix V. Now, 5 times matrix V, right, is 5 times this matrix respectively, right? Where what happens in this matrix product is this operator, this scalar multiple, is going to distribute itself to every single location in the matrix, to every single value found in that matrix is going to be multiplied by the value of 5. This will result in 5 times 1, 5 times -9, 5 times -3, and 5 times 10 in value. You will form a matrix that resembles the respective scalar product of matrix V with the scalar multiple of 5, right? Where in each of these locations you can now perform this scalar product with the components, and this is equal to, in the end, 5 times 1, which is 5, 5 times -9, which is -45, 5 times -3, which is -15, and 5 times 10, which is the value 50. Right? And this, in the end, right, is going to be our scalar multiple of matrix V times the scalar value of 5 in our calculation, right? That is the first type of operation that we can perform with a matrix. Now, another operation we can perform with two matrices is that we can perform their sum or difference calculation. And here I'm asked for the sum of matrix U and matrix V here. If we write down matrix U again, right? Matrix U is equal to the matrix 5, -12, 8, and -4. Whereas matrix V is equal to the matrix again 1, -9, -3, and 10. All right? And we are being asked to calculate matrix U added to matrix V. All right? What we might note is matrix U added to matrix V is the matrix 5, negative 12, 8, negative 4, added to the matrix 1, negative 9, negative 3, and 10. All right, where in this particular case, again, the process is going to feel rather intuitive. You're just going to go through and distribute the sum across the components of each of the matrices, all right, of these matrices. Here we are going to form a single matrix that is going to have 2 rows and 2 columns, where the first row and first column is going to be 5 plus 1 in value, right? That coming from this value of 5 added to this value of 1. The second column in the first row is going to come from negative 12, right, plus negative 9 in value. Now you do want to watch your signs in this process, right? As always in algebra, here we have negative 12 plus negative 9 in value. The first column in the second row is going to come from adding the first column in the second row of each of the matrices. This location, 8, added to this value, negative 3, right? 8 plus negative 3 in value. And then lastly, this, what we might say is the second column of the second row is going to come from adding the values seen in the second column and second row of each of the matrices. So here it would be negative 4 plus 10 in value, negative 4 plus 10. Where now you're just going to simplify those summations if you haven't done so already. I do encourage you, especially when the signs start to get rather complex, to maybe write out your statement so not to confuse yourself. But here you can go through and say, yeah, 5 plus 1 now is 6. Negative 12 plus another negative 9 is going to lead us to negative 21 in value. 8 plus negative 3 is actually positive 5 in value, whereas negative 4 plus 10 is equivalent to also the value of 6. Right? And this result here becomes the sum of those two matrices. All right? Now, we do consider combining these ideas when we look here at part C, where in part C, we are going to consider taking the scalar multiple of negative 3 times matrix U and add that to the scalar multiple of 2 times matrix V. All right? Again, if we write out U and V here, right, U is equal to 5, negative 12, 8, negative 4. And matrix V is equal to the matrix 1, negative 9, negative 3, and 10. And we are being asked to find negative 3 times matrix U added to 2 times matrix V. All right. Now, as we've highlighted, the calculation here is, in these cases, a scalar multiplication and or addition or subtraction of matrices is going to feel rather intuitive in the process. What we might say is this is equivalent to negative 3 times that matrix, 5, negative 12, 8 minus 4, plus 2, and you can see how I'm squeezing together the terms of this matrix. Make sure that you are separating the terms in each of your columns here, right? And that's not 5 minus 12. This is not 8 minus 4. These are two separate values. But this is plus 2 times this matrix V here, where this is 1, negative 9, negative 3, 10. Right? Where, as we've seen with the other two examples, these scalar multiples are now going to be distributed throughout the terms of the matrix, right? The matrix that they're being applied to. So in this first case, it is going to be negative 3 times 5 in the first row, first column. Negative 3 times 5 is negative 15. And you can see, folks, you don't have to write it out. These are rather fundamental operations as long as you are performing them as appropriate you don't have to show out every single step. These are rather fundamental calculations, right? Negative 3 times negative 12, well, that's positive 36. Negative 3 times the 8, that's negative 24. And negative 3 times the negative 4 is positive 12 in value. So to begin with, negative 3 times matrix U is this result seen here, where we're going to add to that now. And notice we are following our order of operations here. The work with matrices and performing just operational calculations with these matrices does follow an order of operations here. Sum and differences come after scalar multiplication. All right? If we distribute the 2 throughout the terms in a scalar product, 2 times 1 is 2, 2 times negative 9 is negative 18, 2 times negative 3 is negative 6, and 2 times 10 is 20. Where we are left with now just adding up the components of these two matrices, the corresponding components. This is going to produce in the end a 2 by 2 matrix, where we are going to take, to begin with, in the first row, first column, we're going to add together these values seen in the first row, first column of each matrix. Negative 15 plus 2, negative 13. Right? 36 minus 18, positive 18. Negative 24 plus negative 6, negative 24 plus negative 6 is what? Negative 30 in value. And then 12 plus 20, right? 12 plus 20 is 32 in value. So here is the result of adding up the scalar multiples of matrix U and V, where U is being scaled by the multiple negative 3 and V is being scaled by the multiple of positive 2, right? We are going to first find their scalar multiples, right, as we've seen in our results here, where once we determine those scalar multiples, we add together these two matrices to obtain this matrix seen here. And again, folks, it's hopefully feels like a rather intuitive process. These operations of multiplication and addition or subtraction are just happening with real numbers, as we've been working with since our early days of mathematics, right? Where we are just now arranging them intuitively in the calculations here involving corresponding matrices, matrix U and matrix V. All right? Now, that's the intuitive process. We are now going to consider, well, what happens if we take two matrices and we start to multiply them together here? All right? If we jump a little further down into our work and we consider these last two cases, right? These last two cases are a little bit more involved here and may not feel quite intuitive. What we have illustrated here are what are known as dot products. This is referred to as a dot product of two matrices, right? That dot being used as a multiplication, illustrating the product calculation that is specific to matrices known as a dot product. Now, what is a dot product is not so intuitive, right? It does involve a bit of a pattern, or what we might say is a bit of a formula, that is referred to oftentimes as row-column multiplication, right? Where even that distinction of the dot product, row-column multiplication, is even a little misleading, because there's, along with multiplication in that process, there is also going to be some summation happening, right? Some adding things up, right? There was a, what we might say, formula given for U dot V or V dot U. If I was to give you that formula explicitly, maybe we say we have the value of matrix AB CD, right, seen here, in a dot product with the matrix W, X, Y, and Z. All right? I'll grab some variable values on different sides of the alphabet here to help us maybe adjust to this pattern, right? But what the dot product of a 2 by 2 matrix with another 2 by 2 matrix is going to produce is what is a 2 by 2 matrix. And I probably should give a little bit of room for these 2 rows and 2 columns to illustrate this formula. You give a little bit more room this way and in this direction. All right? Where we are going to form, as I had highlighted here, the 4 components of this 2 by 2 matrix that is going to be the dot product of the 2 given above, right? Where this first component of their product is going to come from what we call the row column multiplication of the first row in our first matrix with the first column of our second matrix. Where in a row column multiplication, that is even a little misleading, because what we are actually going to do is take the first component of this row and multiply it by the first component of this column, A times W, and add that to the second component of this first row times the second component of this first column, which would be B times Y in value. Right? This first result of A times W plus B times Y is the row column multiplication that's occurring between these 2 generic matrices U and V. Right? Now, to continue that pattern, how we fill in the first row, second column in our dot product, you are going to use the first row of U in a row column multiplication with the second column of V. In a very similar pattern to what we did here in the first row column multiplication. It is going to be this first element of the first row times this first element or component of the first column, A times X. And that is added to the second components multiplied together. The value of B times the value of Z. Right? Now, as you start to work through this formula, you will see that pattern develop. Now we're to fill in our value seen in the second row. It is going to be the second row of U times the first column of V, which is going to go in this location in a row column multiplication. So the first component times the first component. It is CW added to the second component times the second component would be DY, right? And in the last component here, we would do a row column multiplication with this second column, or second row, second column. That would give us the location in the second row, second column of this matrix. So it would be C times X plus D times Z, right? C times X plus D times Z, right? This would be the result given by the dot product of U with V, right? You will note that this does follow a very specific pattern, right? Where the first component of every row is being incorporated into the pattern by being multiplied by the first component of every column in the pattern. And the second component of every, well, that's going to produce these values we see here, right, in some respects. And then that pattern continues, right, throughout both of these matrices. All right. Now, let's look at this specific to our example. All right, you may want to write this formula down somewhere else, or again, folks, it's a pattern. If you can learn the pattern of the calculation, there will be no memorizing of the formula here. And we often say it's just row-column multiplication. So here we might start with U again, which is the matrix 5, negative 12. Let's make sure that's clearly a 5. Negative 12, 8, and negative 4. And we're going to have matrix V be this matrix 1, negative 9, and negative 3, 10. Right? And we're going to consider calculating here what is going to be matrix U dotted with matrix V. It is going to be this matrix 5, negative 12, 8, negative 4 in what we call a dot product with the matrix 1, negative 9, negative 3, and 10. So you can get a pen that works here. You gotta be, this one's still working. I thought I'd exhausted the pencil lead in 2 pencils. I'm almost that case. Here, if we perform these, right, this pattern of calculation here in this example, first row times first column in this location, first row times second column in this location, and so forth, right, with this, right, with these two matrices seen here, it will be the row 5, negative 12 times this column 1, negative 3. That will be 5 times 1 plus negative 12 times negative 3 for the first component. The second component will come from the first column, or sorry, first row, 5, negative 12, times the second column, negative 9, 10. So it'll be 5 times negative 9, right, plus negative 12 times 10. And you can see I use parentheses rather liberally here because I want to illustrate these calculations with multiplication respectively and not confuse them with additions and subtractions and follow a proper order of operations in their calculations. Now, certainly mentally I could probably do some of these calculations in my head, but just to begin with in this first example, I am going to write them out for you. Now, in the second row, that is going to be the second row of your first matrix times the first column of your second matrix, right? That's going to be in a row column multiplication. That's 8 times 1 plus negative 4 times negative 3, right? That's going to be 8 times 1 plus negative 4 times negative 3, right? And that is followed by the row column product of 8 times with negative 9 added to negative 4 times 10. Right? Where now to complete this matrix, that is the dot product of U and V, we just simplify each of these quantities. And like I said, you could have been doing that along the way in your head, but I do caution you, watch your signs as you perform that process, right? It is 5 times 1, which is 5, plus negative 12 times negative 3. Now that product is positive 36, so you're going to be adding on 36 to 5, and that is 41 in value. All right? In this location, it is going to be this first row times this second column, 5 times negative 9 plus negative 12 times 10. But watch the order of the signs there, right? 5 times negative 9 is negative 45. Negative 12 times 10 is negative 120. And if you take negative 45 and you add that to negative 120, you get negative 165 in value, right? There's some signs that you have to keep track of there, folks, and I really do caution you, watch your signs in these calculations. For this, it is given by 8 times 1 plus negative 4 times negative 3. We see that here. This is 8 plus positive 12, right? Well, 8 plus positive 12 is 20. And then seen here, this is going to be negative 72 plus what is going to result here from this product is negative 40, right? Which we can note is going to leave us what? With negative 112 in value. So this becomes the dot product of those two matrices. Now, I do have to, before I run out of video time, can I work through V times U rather quickly here? Let's say we took 1, negative 9, negative 3, 10, and we dotted that with 5, negative 12, 8, negative 4, right? The video runs out of me in 3 minutes. Let's see if I can get this done in that 3-minute time. So it's this times that. 1 times 5 is 5, plus negative 72 is the product of negative 8 and 9. So 5 and negative 72 leave us with negative 68. Now let's do that here. That will be negative 12 plus 36. That's positive 24. Let's do that here. This will be negative 15 plus 80. Well, that is 65. And then let's do that here, right? Negative 3 times negative 12 is 36 plus, we get the product here in negative 40. 36 minus 40 is negative 4 in value. So yes, this is an operation that can be performed rather quickly if you learn the pattern, right? And here is our dot product of V with U in this case. This is vector V dotted with vector U. And you will notice switching the order of a dot product does produce different results, right? Take note, we do see that here. We do get these two different results. And folks, what we are just looking at overall here was looking at performing some fundamental, what we call matrix operations with these two matrices, right? It's a little bit off the beaten track, but we are looking at, in general, just solving systems using matrices. And if we're going to introduce the matrix, we might as well introduce the algebra and the mathematics of these matrices, just to give you some insight into what we call linear algebra. Some of you that are taking those sciences out there may encounter a linear algebra course in due time and off at university, and being familiar with these skills is going to hopefully be useful. So with that said, folks, in a minute left to go on this video, I will stop there, and I'll be back with just a couple more videos to finish out our semester, where we're going to look at some what we're going to call the inverse matrix in the next section, again to familiarize ourselves with linear algebra. And then look at a way of calculating solutions using matrices that might be rather convenient for a lot of you. That will show you actually how to do some of this on your calculator, where you can get an answer to a solution to a system in a matter of just a couple of button clicks. Right? So I will show you that here also in one of the next two coming videos. But with that said, I will stop there, and I hope you're all doing well, and I'll see you in the next one.